In equilibrium statistical mechanics, the famous Boltzmann-Gibbs formula for the probability distribution in configuration space contains everything. It depends on just a few parameters, the most important being temperature. But what about far from equilibrium? We can't expect anything nearly as universal, but it's reasonable to look for various kinds of effective temperatures. Here, we're especially interested in an effective temperature that governs the microstate distribution in some way analogous to the Boltzmann-Gibbs distribution. But should we even expect such a thing, and why? This is the kind of system that got us interested in these questions. This is artificial spin ice. They're lithographically engineered arrays of single-domain magnetic islands on a scale of 100 nanometers, with interactions on the scale of 10 to the 5 Kelvin and barriers to flipping even higher. So it's very tricky to get them into their ground state. This is an MFM image of the same system. The islands which are magnetized up show up as white dots, and those which are magnetized down show up as black dots. So they act like Ising spins, at least as far as the degrees of freedom go. This is a Kagame lattice, which is frustrated, so it doesn't even have an ordered ground state. In the laboratory, we try to get these things into the ground state by rotating them rapidly in a magnetic field that starts at a very high value and is decreased to 0. Now, the result of this protocol is not the ground state, but it's not completely random either. And so we'd like to try to describe that by some sort of effective temperature. These artificial spin ice systems are pretty complicated, so it might be better to discuss something simpler like this ferromagnetic model Z, which works as follows. We pick a spin at random, set it equal to the majority of its neighbors, and repeat. Keep doing that. So here are some examples of simulations of the model that I just described after varying numbers of applications of that rule, and you see that they look a little like the Ising model at varying temperatures, at a time-dependent temperature. Can we describe it by a time-dependent effective temperature? Like this. As we show in our paper, this effective temperature idea can be partially justified and also generalized to an effective interaction. For this model, we take a close look at the evolution rule and find out that we ought to use a nearest neighbor coupling, a next nearest neighbor coupling, and a four-spin coupling. That last one might surprise you. We call this procedure Gibbsianization. We also show in our paper how the evolution rule can be used in a Monte Carlo procedure to track the time evolution of the effective couplings without actually applying the rule in a direct simulation. Here are some results for pair correlations at a certain time for that model Z. The solid squares are the real answer, which come from just direct simulation. The open circles are the best you can do with just the nearest neighbor effective temperature, and we match the nearest neighbor. As you can see, it's somewhat deficient at further neighbors. The diamonds are the result of the Monte Carlo integration of the coupling constant flow that I just described. As you can see, it's very, very good. Thank you for your attention. I hope I piqued your interest enough that you'll now go and read our paper.